I need to inform you that I'm now recording this this session. It's up to you whether or not you put your camera on, but I know for some of you have got broad bandwidth issues, so so you might need to keep your camera turned off. I'm keeping mine turned off because I know that's affecting many of you as well. So we're going to work mostly again from a PowerPoint presentation and a few videos. This would be one where if we're in a classroom, I'd have lots of demonstrations to show you, but we don't really have that facility here in my office. So what we're going to do is we're going to have to do lots of virtual experiments and a lot of thinking about what should happen and what we're seeing. Okay, so we start off with a basic with one basic idea. Why are we looking at thermal energy transfer? Well, the big reason is our topic is actually more to do with energy and ecology. So we have to think quite carefully about how we use our energy and how we save energy. You notice all houses, in fact, all electrical appliances have this sort of energy rating certificate. And what it does is it rates how well a house or an electrical appliance, even in some cases, how well they use energy. It creates like a score. Now, they often have a current energy rating and a potential energy rating. So when somebody comes to assess the energy efficiency of a house, that looks at what is currently in place and what could reasonably be put into place. So obviously, if you're selling a house, you want to try and make sure that your current energy efficiency is as close to the potential as you can manage within reason. And you have to make decisions about that. So what you have to do is think about how you can make your home more efficient. So here is how heat moves by convection, okay, through a house, and by conduction, and also by radiation. You can see how much energy is being lost through the windows, through the roof, through the walls, through the floor, and indeed through the door. Now there are things you can do. So you can put cavity wall insulation. If you put an extra layer of insulation on the walls of the house, it stops that 25% from escaping. If you put in loft insulation, that might stop some of that 35% from escaping. So every time you think of things that you can do to a house to reduce the heat lost from a house, what happens is that you can reduce the amount of heat being lost, and therefore you're reducing the amount you're paying to actually heat up the house. So there is a good economical reason, although some of these methods are more cost effective than others. So for example, if you put in low energy lighting instead of the old fashioned sort of filament bulbs, you'll save yourself £11 per year on your electricity bill. The thing to remember though, is if you were to replace all your bulbs in one go, it would cost you between £30 and £50. Let's say it cost you £33. That means if you save £11 per year, it takes 3 years to pay back the amount that you spent on installing the newer low energy bulbs. If, on the other hand, you fit a hot water cylinder thermostat, so where you've got a hot water tank, if you've got a device there to control the temperature of the hot water tank, you'll save yourself about £100 on average per year in fuel bills. Well, it costs to fit one of those. Well, it'll cost you a couple of hundred to put one in, so that pays back within a couple of years. But if you were to put in something like solar photovoltaic panels, that will cost you a few £1,000s, which means it will take you many years to actually pay back the amount you've actually paid for it. So sometimes the energy efficiency measures put in place, like double glazed windows, for example, well, I can tell you it cost me £6,000 last time I had double glazing fitted to a house, and it only saves you £30 per year. Well, that means it's going to take a couple of 100 years to actually be able to recoup the money that you've spent on getting it fitted. So some things are cost effective and some things are not. But it's also the environmental concerns to take into account. If you're using a lot of energy, you're putting onto carbon dioxide into the atmosphere, which contributes to climate change. So that's a basic idea of improving the efficiency of a house. But what we're going to do is we're going to look at the heat flow through a fluid. Now, a fluid, remember, is a liquid or a gas. And we're going to look at how heat does travel through fluids. We know it doesn't conduct very well through fluids because we learned last time that really you need a solid, preferably a metal, for conduction to happen efficiently. But you can heat up liquids and gases, so there must be a way that they actually do transfer that thermal energy. So we're going to have a look at exactly why that is, and we're going to introduce the idea of convection. Oops, gone past. There we are. So to introduce the idea of convection, I've got a rather corny, rather a cheesy video to show you. It's a little bit corny. It's quite old-fashioned, but the actual physics behind it is very sound, and I think it explains it rather well. So I'm just going to ask you to watch this. It's only a couple of minutes long. If it works.
Eureka! The story so far. Objects immersed in a liquid are buoyed up by a force equal to the weight of the liquid displaced. This is called the principle of buoyancy. If the object has the same density as the liquid, it will float in the middle of that liquid. If it is more dense, it will sink to the bottom. If it is less dense, it will rise to the surface. And now, convection. You look nice and warm. Where does the heat for that hot water radiator come from? The furnace, of course. In the basement. Why is the furnace always kept in the basement? Why couldn't it be in the attic for a change? What would happen if it were? Anyone on a floor below would freeze. That's what would happen. Why is this? Well, let's put the furnace back where it belongs so that we can see how a hot water heating system works. The furnace heats the water in a tank. The hot water rises up through these pipes and into the radiators where it cools, and then the cold water flows down through these pipes and back into the tank where it is heated up again, and so on. But why does hot water go up and cold water go down? Because of the principle of buoyancy. If you hold something that is less dense than water, such as a cork, in the middle of a beaker of water, the buoyant force pushing that cork up will be greater than the force of gravity pulling it down. And as soon as you take your hand away, the cork will rise to the surface. Now, when water is heated, its molecules speed up and it expands and becomes less dense. And this less dense water will therefore go up and then cool and become dense again and therefore go down. And that's exactly how hot water heating systems work and why your furnace is in the basement. But the house next door hasn't got a hot water heating system. It's heated by means of hot air. And yet, your neighbor's furnace is also in the basement. Why? Because the principle of buoyancy applies as much to gases as it does to liquids. When air is heated, its molecules speed up, and it expands, and becomes less dense. And so hot air rises, just as hot water rises. That's how hot air balloons work. When the air inside the balloon is heated up, it expands. And therefore, there's not enough room for all of it inside the balloon. So some of this hot air escapes. The result of this is to leave fewer air molecules in the balloon than before. In other words, the air inside is now less dense than the air outside. So the balloon floats upwards, just like the cork in the beaker of water. The fact that hot air rises also comes in useful when cooking a hot dog. It'll take forever to get hot if you hold it beneath a fire. But if you hold it just above the hot air which is rising up from the fire, you're in business. And this is why your neighbor's hot air heating system is able to work on the same principle as your hot water heating system. Hot air goes up, it cools, and the cold air goes down. Since the behavior of gases and liquids is so similar in this and many other respects, and since both gases and liquids flow, scientists refer to both as fluids, and to the type of heat transfer which carries or conveys hot fluids upwards and cold fluids downwards as convection. And it's thanks to convection that balloons go up, hot dogs get hot when you hold them over a fire, and one furnace in your basement is enough to heat your whole house.
Okay, did that make sense? Did that make sense?
Yes.
Okay.
Yes.
Okay, so got a question.
Yes.
Here.
Yeah.
Excellent, excellent. Thank you very much. We got a question here. Got a smoke chimney. We've got a candle, and we've got somebody here with a lit splint they've put out, so it's making smoke. What do you notice is happening to that smoke? Anybody?
That's right.
It's going to the candle.
It's going towards the candle. So the smoke would normally rise, but here it's going through the candle. So there must be air pulling that smoke down here. So why is it being pulled down?
Because the fire might be absorbing the air around it.
Right. But what's causing the air to go down here?
The gravity.
Well, gravity. Well, if the air's the same density as the air around it, it shouldn't really sort of rise or fall. But what's this candle doing to the air here?
Absorb it.
Oh, it's using some of the oxygen, but what's the candle producing?
Light? I don't know.
Well, it's producing,
Carbon dioxide.
what happened if you held your hand over a candle?
Oh, heat. It's producing heat.
Right, it's producing heat. It's heating up the air. So we know now from convection from the previous video that hot air will rise up through cold air. So the hot air is going up here. So what's happening is that the cold air here is being pulled down because the hot air is rising, reducing the pressure here. So the atmospheric pressure is pushing air down this chimney and towards this candle. And so it's creating a convection current. Now, back at 100 or so, 150 years ago or so, you guys wouldn't be in a classroom. Well, certainly in the UK, you might be put, instead of being in a classroom, you might be out in a coal mine, working in the coal mines. The trouble with a coal mine is they're underground. So imagine this bit here is the coal mine. If you've got people working down here, they're going to run out of oxygen. So to ventilate, what some of the coal miners used to do, they'd light a fire under one shaft. Remember that, if you think of that as being the surface of the of where the mine is, that's the ground level here. The mine shaft drops. The mine shaft has a fire underneath it. The fire actually heats up the air around the fire, which goes up the mine shaft and pulls in fresh air down another mine shaft. And so that way you could use a fire to keep a coal mine ventilated. Now, to show you some other demonstrations, another demonstration here. I've got a beaker. It's being heated by a Bunsen. And the same thing is happening to the water here. This water has a little bit of a solid which slowly dissolves in water called potassium permanganate. When you put it in water, it turns this lovely sort of purple color. Now, as you heat up the water here, what happens is the water becomes less dense than the water over here. And so it rises. When it gets to the top, it's got to go somewhere. So it goes across the top. As it goes across the top here, it starts to cool down because it's conducting through the glass walls and through the surface here to the air, and will eventually sink back down. And so you end up with a circulating current of water called a convection current. And this is quite important because if you think about it, if you make yourself a hot drink, your heating element is always at the bottom of the kettle. And the reason why it's at the bottom of the kettle is because the heating element heats up the water by conduction from the element to the water. And then that hot water, being less dense than cold water, rises up and is replaced by the cold water. So in your kettles, when you're making yourself a hot drink, you can actually, you get a convection current, which enables all the water to be heated up. In fact, if during your break, if you make yourself a hot drink at any time during a break or during the weekend, you'll find that your, just a second, you'll find that that when you look at the water, you get a weird sort of ripple effect, and that's actually the hot, less dense water rising up through the cold water, and because it's less dense, it bends light in a different way, and you end up with a sort of a weird effect. Okay, right. And so, if you think about it, if that hot water is represented by this potassium permanganate solution, what happens is the hot water rises and cools, and you end up with all the water being heated. So the reason why we have convection is because the fluid, which is a liquid or a gas, is heated, the particles vibrate more, and they become less, they spread out, making the liquid become the fluid, the liquid or gas, become less dense, and that then rises through the colder liquid or gas. Okay. So just to show you another demonstration of this, I've got a nice little video demo. I'm hoping it'll work. There we are. So let's just watch this, and we can see it in action again. Hoping we don't get an advert beforehand. If we do, I apologise. So we've got two glasses here. One's full of this liquid that's been coloured red to represent hot liquid, and this one's got green or blue particles in it representing colder fluid particles. And they're separated at the moment, but as soon as you try to mix them, apart from a mess, you notice that the hot, less dense liquid rises to the top, and the cold, more dense liquid falls to the bottom because it's more dense. Okay, let's move on. So, if we think about it, if we think about the applications, if we've got a draft excluder, do you know what those of you who know what a draft excluder is, what does the draft excluder prevent? Anybody in a house? I'll give this one to Ari.
I'm not sure what draft excluder is also.
Well, a draft excluder is something you fit to door frames and to doors and windows, and they create a good seal around the window so that no.
Is it to prevent like cold from outside to come in the house, or to prevent heat or something?
Yep, that's correct. Okay. A quick question for Christopher. What's a fluid? Sorry, can you say that again? I couldn't quite hear you.
So do we need to write this?
No, I'm just asking you. We're just
okay.
it. So what's a fluid, Christopher?
Fluid is like a liquid, some.
The liquid or a what?
Like a gas.
Or a gas. Well done. Good. Well done. Okay. Now, I can tell you from number 3, I will give you number 3. The Earth's plates are actually moving because you know the structure of the Earth. In the structure of the Earth, you've got underneath our solid crust, you've got a mantle and a liquid core. Now that liquid core is very hot. So what happens is you get convection currents within that core. The hot molten rock rises up, and as it cools in that convection current, it drags the Earth's plates on the crust around. So it means that it moves the North and South American continents away from the European and African continents at a rate of a few centimeters every year. So the plates are still moving. It also pushes India into the rest of Asia, and that movement of the plates is actually causing Mount Everest to become taller by a few millimeters every year as well. Okay, who am I going to pick next? Freddie, what happens to the warm air from a radiator? In your room, you may have a radiator. It's warming up the air around it. What's going to happen to that warm air? Freddie, are you there?
Yeah, sorry, it was just glitching. I couldn't unmute myself.
Yeah.
What happens to the warm air? Does it are you talking about after it cools down, or?
As soon as it's warmed by the radiator, what happens to it?
Well, it's released, isn't it?
What do you mean by released?
Like it goes into the air and heats up the room.
Yeah, but how does it get around the room? Because remember, air is a very poor conductor. So how does the air actually travel around the room?
I'm not sure. Sorry.
Well, if it gets hot, it's going to become less dense. So what will the warm air around the radiator do when it's in the cold air from the rest of the room?
I'm seriously not sure. So.
Well, it'll rise. It'll rise. So it rises up from the radiator. And when it gets to the ceiling of your room, it's going to move across the ceiling. And as it cools, it'll come back down the other side of the room. So you end up with a convection current. Okay. And the cold air sinks because it's more dense. Okay. Right. Now, what I'd like you to do is using the chat window, I'd like to rate your understanding of convection so far, red, amber, or green. Okay, so go to the chat window in Zoom and rate your understanding as red, amber, or green. Right, Christian? Oh, Christian seems to have logged out. Christopher, have you rated your understanding?
Pardon?
Have you rated your understanding in the chat box in Zoom?
Amber.
Okay. Name?
Yes.
Have you rated your understanding?
Yes, sir.
Right, okay, I've got you there. Okay. And Jethro, what's your understanding? Red, amber, or green so far this lesson? Jethro, are you there? Jethro?
Yes,
What's your understanding? Red, amber, or green?
amber.
Okay. Right, so let's move on. Let's just recap that then. I think most of you are amber, so you've got a basic understanding, but I think you're not very confident so far. So let's just have a quick think about how this works. So what I'd like you to do is, on a piece of paper, I'd like you to try and answer this question. So if you're red, you really don't get it, just describe what you're seeing in this picture. If you're amber, try and explain why it's happening. If you're green, you should be using keywords such as density or dense, current and convection in your work. Okay, I'm going to give you 6 minutes to have a go at this, okay? So on a piece of paper, piece of scrap paper, just write it down and then I'll ask you to read that out. I may ask you to read that out in your after the 6 minutes. Alexa, set a 6-minute timer, please.
6 minutes, starting now.
Okay, starting now. I'm just going to pause my recording while it's doing that. Alexa, stop, please. Right, so I'll set you a little task there. So this would be worth 6 marks. It's quite an open-ended discussion. So you've got a picture here of a convection current happening. It's the air circulating around the room. It's actually the hot radiator that's driving it. So what would I be wanting to put in? So the first thing I'd want to say is the radiator increases the temperature of the air around it. Okay, whoops, and I've spelled radiator correctly. Okay, that would be worth 1 mark. You would also then say, well, if the air around the radiator has been had its area and its temperature increased, the particles in the air spread out because they vibrate more. Okay, the air becomes less dense. Okay, so the air rises up. The air behind it pushes the warm air across the room. Whoops, spell it correctly. And so if you've got the air around it pushing, can you all see this text, by the way?
Yep.
Okay. so the air around it pushes, so the air behind it pushes the air, warm air across the room. Warm air cools and falls, okay, or goes down. And then you'd say cool air then travels across the floor. The last thing you'd want to say is to identify that this is a convection current. Okay, so for each one of those 8 points I've made there, I'd like to look down at what you've written. And if you've said any one of those points, you get a mark, okay? For a maximum of 6. Although there's 8 points you could make, if you get 6, 7, or 8 of those 8 points, then you get a mark of 6. So what I'd like you to do, you've got about 1 minute, I'd like you to assess what you've got written down in front of you, okay? And write your mark in the chat box, please.
Sir?
Yep.
I'm just going to use the bathroom quickly, if that's okay.
Yeah, that's fine. I've seen your marks there. Well done, Freddie.
Okay, thank you.
Okay, so Ari, Chris, and Freddie, if you just put your, sorry, Ari, Chris, and Zane, if you just put your mark out of 6 in the chat box in Zoom, and then we'll move on. Okay, Zane, 4 out of 6, well done. Well done, Ari. 6 marks. That's good. Okay, Christopher, you there? Okay, no response from Christopher. I'm going to move on because I think otherwise we're just going to be sitting waiting for a long time. So let's let.
He got 4. He got 4 out of 6. So.
All right, I didn't see that. Is Christopher with you then?
No, he sent it to me by accident privately. He forgot
right.
to send it to everyone, so it says 4.
That's great. Okay, so let's now move on. So the same happens with convection in your refrigerator. If you've got a fridge freezer, it's got a refrigerator and a freezer compartment above it. And it's above the refrigerator for a good reason. It's the fact that if you've got your freezer compartment at the top, what happens is the cold air from the freezer compartment can then keep the rest of your refrigerator cool. So that's how convection current is often set up inside your refrigerator as well. And it's why your freezer compartment is often at the is often at the top of the refrigerator, because that's actually the part that keeps the rest of your fridge cool. It does it by using these convection currents. Right, let's move on. That's convection. The next one we want to talk about today was thermal radiation. And we've got here a simple question. Which one of these two cups would keep your coffee warm? Any ideas?
Cup 1.
Cup 1. Why would cup 1 keep your coffee
It
warm?
has less surface area, so less heat. Less
Good.
like from the surroundings, less can go onto the coffee.
Okay, that's good, because you know that if you've got less surface area, then you can't transfer that thermal energy to your surroundings quite as efficiently. But we're going to look at how the color might also affect the transfer of thermal energy.
Doesn't black black stuff absorb more heat?
It does absorb heat very well. It also emits it very well, as we're about to find out. And there's a simple way to remember to remember this. We're just going to make sure that we can state how infrared radiation is used. We can look at that's called thermal radiation. We sometimes call it infrared. And we're going to have a look at the relationship between hotter objects and the level of infrared radiation. And we're talking about which types of surfaces are good absorbers and emitters and reflectors of infrared radiation, and describe why it can travel through a vacuum. We're actually going to hit that one pretty much first. So one application of infrared radiation is it's how energy travels from the sun to us. Now I've got here solar heating cells. Solar photovoltaic cells that produce electricity, and also some that produce hot water. The trouble with the hot water solar collectors in Britain is we don't get a lot of direct sunshine. So often with a lot of clouds, it doesn't work terribly well. You need direct sunlight. But if you're in a hot country, you'll see many hot countries, they have a solar collector on the roof, on the roofs of many houses, because it collects the radiation from the sun, the infrared radiation from the sun, and that is then used to heat up water, and you can actually collect hot water for free. So again, I'm going to show you your last Eureka video, which will explain how this works. Okay, so I'd just like to watch this again. It's only a couple of minutes. We're doing lots of different little bits and pieces here today. So I'm just going to watch this for a couple of minutes, and it'll explain what thermal radiation is.
Eureka! The story so far. Whenever there is movement and friction between two objects, you get heat. This is because the movement of molecules and heat are really one and the same. But we know that movement is a form of energy, so it follows that heat itself must also be a form of energy. That's why heat, just like energy, is measured in joules. And now, radiation waves. If you touch something that is very hot, you'll get burnt. This is because of conduction. The heat is conducted by a sort of domino effect from molecule to molecule, or from atom to atom, along the hot object and into your fingers. That's one kind of heat transfer. But if you hold your other hand above the same hot object, you will also get burnt. This is because of convection. The hot object causes the molecules of air above it to speed up. The hot air expands and becomes less dense, and is therefore conveyed upwards. That's a second kind of heat transfer. Are these the only two ways that heat can be transferred? Then why are you sitting under that beach umbrella? Because the sun's too hot? But how can the sun transfer heat to you? You're not touching it, so there can't be any conduction, can there? And since most of the space between you and the sun is just that, space, except for the thin layer of air formed by the Earth's atmosphere. There can't be any convection either, can there? Because once you get beyond our atmosphere, there's almost nothing out there to do the convecting. But the sun still feels hot. Amazing. How is that possible? Is there a third kind of heat transfer which allows heat to move through empty space? Yes, there is. And to understand it, you must first of all remember that heat is a form of energy. Now, energy can travel in various ways, but one of the cheap ways in which heat energy travels is in the form of waves. Rather like the waves that a boat makes when it moves through the sea, or the waves that spread out when you drop a pebble into a pool of water, or the waves that travel along a rope if you jiggle one end of it up and down. In all these cases, what you are seeing is the effect of the movement of energy itself. By means of waves, energy can move through any distance. You can do it yourself. You can make that umbrella move without touching it. Tie one end of your rope to the umbrella, and now move your end of the rope up and down. You can actually see that your energy is traveling through the space between you and the umbrella, and then making the umbrella move. Energy from the sun travels like that. The sun sends out waves of heat energy in all directions. Each of them is rather like the spoke of a wheel, and this is exactly what scientists call them, only they use the Latin word for spoke, which is radius, from which they get the word radiation, the name given to this third kind of heat transfer. So it's by means of radiation waves that the sun can transfer its heat energy to you and make your molecules go faster and therefore make you hotter, even though the sun is millions of miles away. Just as by means of waves again, you can transfer your energy to the umbrella and make it move, even though you're standing several meters away from it. But it isn't just the sun that radiates heat in all directions. So does an ordinary fire, or a stove, or an electric light bulb. In fact, waves of heat energy are radiated to some extent by all sources of heat. Even you radiate a certain amount of heat in the form of waves. Come to think of it, there are waves everywhere. Oh, watch out. Here comes a big one now.
Okay, so everything that's hot emits infrared radiation. So, but some surfaces emit it better than others. So for example, here I've got a Leslie's cube. Now this Leslie's cube can be filled up with water and it's got 4 different surfaces on the outside of it. So but because they're filled up with the same hot water from the top, it means the actual temperature of each surface is the same. But watch what happens when you try to measure the infrared radiation or thermal radiation from this cube.
This metal box is called a Leslie's cube. All the surfaces are the same material, but they're different colours. I'm filling it with boiling hot water. Now I'll use a special thermometer, an infrared thermometer. It takes the temperature of surfaces by detecting the heat radiation from them. Let's test the white surface. That's 49.8 degrees C. Twist the cube around so that I can test the silver surface. It's 27.3 degrees C. That's quite a lot cooler. Now I'll test the black shiny surface, which is 68 degrees Celsius. And finally, I'll test the matte black surface. See if that's different as well. 66.3 degrees. As we watch the video through again, this experiment creates a few questions for us to answer. Why is it that the infrared thermometer records different temperatures for the different surfaces of the box? You can trust me, if you touch them with your finger, they'll all be hot. Why is it that the measurement of the temperature for the silver surface is significantly cooler than for the black surfaces?
Right. So from this Leslie's cube, you had 4 different surfaces. You had a shiny black surface, a matte black surface, a shiny silver surface, and a white surface. And what they showed there was that the shiny silver surface actually and white surfaces emitted less thermal radiation than the black surfaces did, and the dull surfaces did. So what that meant is that different coloured surfaces are better or worse emitters of thermal radiation. It's a bit like, if you see it, you can see it in the outside world, and we'll have a look at some outside world applications at the end of this lesson. You often see things that objects we try to either heat up or cool down are often painted black because they're good absorbers and emitters of thermal radiation. That's why if you wear a black t-shirt out on a sunny day, you'll feel warmer than if you wear a white t-shirt. And in fact, it's the reason why a lot of people in hot countries paint their houses white, to reflect away that infrared radiation. So I'm aware I've been talking a rather long time, so I'm not going to go through these videos simply because I think you guys are getting a bit I've probably had enough of me talking by now. So we're just going to go through this. So everything that's hot emits thermal radiation, even we do. At the moment, in many airports around the world, there are thermal imaging cameras, and the thermal imaging cameras are there to measure the temperature of your skin. The hotter you are, the more thermal radiation you're emitting. So this gentleman here is walking through an airport. If we look at the color of his skin on here, he's round about sort of 35, so he's okay. But if somebody's skin was showing white or yellow on this camera, they would mean that they're running a temperature and they have a fever. So we can use thermal imaging to measure the temperature of things without touching. We can also use thermal imaging to find things in the dark. The police often use thermal imaging cameras to track stolen cars and to track thieves as they're trying to run away, because even at night they're emitting thermal radiation because they're hot. We also use thermal radiation to transfer heat. So for example, this piece of toast, if we think about it, there's air in between the heating elements here and the toast, so it doesn't conduct, so the heat doesn't conduct very well. The hot air around the heating elements are going to rise up out of the toaster. So the only thing actually making the toast is actually a thermal radiation or infrared radiation being emitted by the element here and being absorbed by the bread. Okay. So I'm just going to skip that a little bit. Okay. Infrared radiation can travel through a vacuum because it's a wave. It behaves almost exactly like light. And we can use that infrared radiation from the sun, again, as I said at the beginning of this section of the lesson, to actually heat up water to then store it in a tank. Okay, so let's have a look at a couple of examples before we finish. So here we've got a car radiator. The car radiator here, it's got lots and lots of little fins, and it increases the surface area. It's also painted black because black is a good absorber and emitter of thermal radiation. The car radiator's job is to have hot water flowing through it so that it can cool the hot water down to a lower temperature to stop the engine from overheating. So it's painted black so that there is more radiation being emitted by it. If you are in a hot country, you're wearing white clothes. The reason why a lot of people wear white in hot countries is because, just like light, white clothes reflect light. That's why they look white. That's why they're bright. They also reflect infrared radiation from the sun, which helps these gentlemen here to stay cool. These solar panels on people's roofs, next time you're out and about, look, if you see people's roofs with solar panels on them, you'll notice that they're black because black is a good absorber. If you have somebody at the end of a marathon, or if they've had to be rescued off the side of a mountain because they've got hypothermia, means their body temperature's, their body's gone cold, they'll sometimes be put in a foil blanket because the shiny surface will reflect the body heat back towards their body instead of allowing it to escape. So it helps to keep them warm. Often cooking hobs use thermal radiation to actually heat up pans. People who need to store oil. Oil is obviously very flammable. So one of the ways of stopping something from stopping the oil from getting too hot and possibly catching fire is to make sure the tanks they're stored in are a nice light colour like silver. Cricketers, it's one of the reasons why cricketers wear white clothing, because they have to wear a lot of pads, they have to wear full-length trousers, and sometimes they do cricket in countries which are very hot, which means that they would get very hot, so the white reflects the sun's rays away from them. Some people wear dark clothing in order to get warm. So this lady here, although it's a sunny country, she's actually on a part of her country which is in a mountain, which is very cold. So she's wearing black so that she can absorb the sun's thermal radiation and get warm. And many houses in hot countries have shiny metal roofs. So I was going to set this homework, but looking at today's lesson, I'm going to set you something slightly different. So if you bear with me for a second, I'm going to set you a different task. So if I go on to, bear with me. If I go on to onto Satchel, and we look at your homework task for today, what I would like you to do, I'm not going to ask you to do the homework attached, okay? We'll maybe skip that one, and we'll do that when we come to look at energy conservation. But what I'd like you to do is to do this last Seneca activity. It's quite a high level one, but it's all about conduction, convection, and radiation. And then next lesson, we'll put all those together. I've recorded this lesson and I'll post it up on this page when I get around to editing it. Okay, so you've got about 10 minutes to make a start on the Seneca task. I reckon the Seneca task will take you probably 20 minutes at the most if you do it properly. Okay, I will see you all next week.
Okay, thank you, sir.
I guess I have a good day.
Take care.
Goodbye.
Bye.